All right. This part we will be doing a demo on how to do batch processing for like INSAR data using GMTSAR. Over this part, we'll be doing like two demos. One of them will be doing for like a earlier SAR data using ALOS data. Then the second part will be about doing with TOPS data. Since some of the processing steps might take a while to run, so when you see the video, it might be clipped a little bit, edited, so that to save some time. But sort of you can like follow each of the steps to finish batch processing using GMTSAR with this video, I hope. So we're gonna start with like searching the data. This is the ASF data vertex. If you go there. For example, we want to search for ALOS data, which will be our first demo. You can click over here, pick ALOS PALSAR, and we're gonna zoom in to maybe draw a box somewhere, maybe here in the creeping section. Then we can click on the filters, and we want the 1.0 data, which is the original data, and then we can click on search. Okay, has tons of data covering here. Let's try to pick maybe, I don't know, maybe this one ascending acquisition over here. It belongs to past 220, I think. We update it over here and do the search. Okay, now we have maybe 3 frames. This one seems to be crossing the fault very well. Maybe we'll just pick this frame. The frame number will be 710. All right, then we have pretty much a stack of data. You see that I have something in my downloads in my cart. I'm going to do a clear. Then you can just click over here to put everything into your cart. And once you want to download, instead of directly clicking on each of them, you can do this download the Python script. And after doing that, you get a script downloaded. Let me try to, oh, it's still downloading. Okay, there we go. This is a Python script. I opened it in text editor, and you can see a bunch of lines. But basically, you can just run the script to download all the data. Well, usually when you're doing this step, you are also going to try to figure out, for example, the longitude and latitude from your top left corner, and then try to make a DEM using the coordinates you find out on this map. But we're going to do it in a slightly different way, like try to assume that we don't know where this data set is. All right, let's close this. And let's copy this downloading script here. And then basically you can just make it executable and then just run it. I'm not going to really download it all here because in order to save time, I have already downloaded some of the data set in this data directory. If you do ALOS -L, you'll find out, oh, I have 5 of them downloaded here already. So I'm not going to rerun the download. Instead, I'm going to directly process this data set. You can see it's also 710 in the frame number over here. And next, what we're going to do is that we're going to go into this directory and see what's inside, or maybe just do ALS. You see inside there are this LED file, which is the orbit, and also the imghh, which is the data file. So what we're going to do is that go back to your main directory. Let's delete this downloading script and make a directory called raw. Oops. Go to this raw directory. We're going to do the all the pre-processing stuff over here. What we're going to do is that we're going to link /data img whatever. Actually PALSAR whatever and star slash img hh star dot to finish the linking. And we could do the same thing for the LED file. So we have all the data files here. Oh, maybe this is too small. Let me make it larger. So we have all these data files located in this raw directory. And then we're going to do the pre-processing. The first step we're going to do is that, sorry, let's go back to the raw directory. We could do ALOS, img, whatever this data file, and into a list. Maybe call it image list. And then we're going to move this image list to the upper directory. Let's come back here. So what we're going to do is that we're going to use this script called batch processing. If we just run this without any argument, it's going to tell us how to run the script. You see, we have a lot of instructions listed here, but basically it's calling this to do batch processing in GMTSAR. Basically, it's calling this script again and again to do each of the steps for batch processing. And inside, it is actually calling the P2P processing again and again to do each of the steps. For example, it says, okay, step one, if you want to do pre-processing, we should find a list. If you're doing TOPS data, you'd also need orbit files to be listed. And it also gives an example here. For example, for ALOS data, the list should be looking like that, which is just the image list we created right now. So we're going to run this very first step and see how it goes. The argument are satellite name. So we're going to use ALOS here. And also the master image. For now, we're just going to assume that we're going to use the very first image to be the master image. You're going to give it a list, which is a list we just created. And then we're going to run step one. You can create a configuration file with pop config, or you could just leave it blank, and it's going to create one for you. So we're going to do it over here and try the very first step. So we're going to do batch processing, ALOS. Oh, we don't know the master image yet, sorry. So we're going to cat this image list and pick the first line to be the master image. And we also need the image list. We're going to do step one. So we're going to leave it running. Okay, this is calculating the Doppler for the master image. Then it's also processing the rest of the images. You see it's saying it's converting aligned image from FBD to FBS because for ALOS processing, you need to pick a, you need to pick an FBS data so that it has more sampling along the range direction. Yeah, it is running. Oh, all of them are done. That's pretty fast. And so after it's getting done, yeah, it created some directory, but I guess SLC is blank. Yes. And raw directory has some more stuff. You see it has this orbit extracted over here. And this is the parameter file, which is called PRM file, and also the .raw, which are the raw radar echoes being stored in this data file. And apart from these new files, you also get this baseline table.dat, which stores all the baseline information. If we do a cat raw baseline table.dat, you see that it listed all these acquisitions and their acquisition time in terms of year of day, and fraction day, and also a date a date count starting from a specific date. I don't know the exact number, but it accumulates with time. And then you have the parallel and perpendicular baseline being stored over here as well. And also you have this kind of plot, which is baseline.pdf. If we open this baseline.pdf, this should be raw baseline.pdf. I'm going to bring it over. You will see that we have 5 images. We pick the first one to be the so-called supermaster image, and these are the rest of them. The vertical axis is baseline, horizontal are year. It looks a little bit odd because ALOS is known for its problem of drifting orbits. You see that it actually drifted from here all the way up to here and then get settled and then drifting again. So in order to pre-process, in order to align the data, actually, sometimes you cannot do a one-step alignment. In other words, you might be able to align these two images to the supermaster image, but you cannot directly align these two to the master image and expect them to be able to create interferograms with the master image. So what we're going to do is we're going to do a two-step alignment. So we're going to align these two images to the master image. So let me draw a little bit. So we're going to align these two directly to the master image, and this one to the master image too. Then the second step will be to say we're going to align this image to this already aligned image. So sort of like a secondary alignment over here. I don't know why this one turned red, but you sort of know like what we're going to do. So in order to do that, we also need a line list. In other words, we have this image list, right? But remember that when we check on the batch processing nodes over here, for step 2, you also need an input file sort of look like this, sort of like the first file, but assuming the very first line is the supermaster image, then it's going to align all the rest of the images to the supermaster image. But also it says over here for secondary alignment, run this step multiple times by setting escape master being 1. In other words, we assume the master image is already done, then perform secondary or tertiary alignment. For this step, for the very first run here, we're going to just run it normally. And the second time we run it, we're going to like put the escape master to be 1, so that assume this one is already done, and we're only align this image to that image or secondary master, we call it sometimes. All right, let's put it over here and make it smaller, just for reference. And we're going to create an image list, a line list, sorry. Add image list into align list 1. Remember that we don't need the very last one to be aligned to the supermaster image, so we're just going to delete it. And for the second list, we're gonna keep this one, which is the third one in the line, to be the secondary master. Then we're going to align this image to the secondary master image. Again, what we're gonna do is call this batch processing script one more time. We're gonna set to be ALOS. Oh, master image. Guess it's this one, and align list 1. 1. Oh, step should be 2. Sorry. And you also see that we have a config file here, which is generated by sort of the automated processing. We're going to use this config file then to run the processing. Okay, started. It's gonna like start focusing the master image, and then the secondary, the aligned images and the secondary master image as well. It's gonna take a while to run. Okay, I rearranged the window a little bit, and you see that the first image, the master image, has finished processing, and then it's running the first aligned image. It's doing the focusing, and now it's doing what we call cross-correlation to try to co-register 2 images together. After this is run, it's going to resample the aligned image to the coordinates of the master image. So after doing this co-registration step, the images should be having pretty much exactly the same size. All right, things are done. As you can see, it actually went through processing the master image and then doing for the aligned images and doing cross-correlation and resampling the data and doing it 3 times. So we finished the very first step of doing the co-registration. Let me try to clear this a little bit. And we're going to do for the second step, which means we're going to co-register this image to that image. But before we do that, we are going to do a edit this config file we're going to get into it and then set this skip master to be 1, which means we're only going to work on the aligned images. Let's do some cleaning. And the next step will be running on this batch processing, ALOS. Sorry, let's add the align list 2 first. And this time we'll be using this image to be the secondary master image. And copy it over here. Then we're going to give it the align list 2. We need to put the config file here so that it knows you're going to skip for the master image. You don't want to run this one more time because this is already co-registered. It's getting shifted a little bit. Let's hit it run. Oops, wrong step input. Oh, I didn't put in which step to run. This will be the second step again. All right, this is done again. And you see that it only processed the align image. It didn't do anything for the master image, only processed one of them. If we do ALS SLC, you see that these are all the files getting generated during the alignment step. If we do a SLC star SLC minus L, you see that all these images have exactly the same size. That's what's supposed to happen after co-registration. All the images are having the exact same size as the master image. Sometimes the master image could be off a little bit, having some like a few extra lines, so the size is a little bit different, but that's okay. So next step will be doing a DEM construction. If we go to the topo directory, what we're going to do is that we're going to run a make dem.csh to download the DEM. But before we do that, we need to figure out this east-west, south-north boundaries. And to do that, we're going to go back to the raw directory, and we're going to do a set baseline, basically computing the baseline info for any two of the images. You see that it's popping up all these numbers for like baseline information, where it started, where it's ending, parallel, perpendicular. But what's more important is actually this two numbers here. That is a long type point and latitude type point, which gives you a rough coordinates for the center of the image. So we're going to use that information. Let's go back to topo and run this make dem.csh with setting, for example, maybe just 1 degree and 1 degree on each side of this point, because we know for ALOS data, typically it has a swath width of, I don't know, maybe 70 kilometer and has a length about, I don't know, 90 kilometer. So like 1 degree on each end should be able to cover the image. So we're going to use number here, negative 121.5 and negative 119.5. And for latitudes, we're going to use 34.8 and 36.8. And you see that you have two modes to choose from. One is SRTM1, which is a 1 second. The other is 3. I mean, in order to make things run faster, we're going to use 3 here. So we're going to put in mode 2. But in order to get a better like a DM or higher resolution DM, you pretty much want to use 1 for these swaths or street map mode data. If we hit run, it's going to try to fetch data from the Hawaii server. This runs really fast because I used to download data from this region, so it's stored locally already. But normally it takes a while to try to get data from the Hawaii server and try to piece everything together to make you a DEM file. The next step will be to run the batch processing again. But before we do that, let's look at the config file one more time. Instead, there's actually a parameter where you can set the topography interpolation mode. Normally, it's going to run surface with tension. It runs a little bit slow. And if you don't want to waste time waiting for that, you can also change it to 1 to do triangulation among all the data and try to create a model using that. I mean, the surface is being tested for a very, very long time and it's very stable. So normally you're going to choose 0 for that. But in order to just show you guys, I'm going to use 1 here temporarily. So we're going to do batch processing. we need to know the master image one more time. Add image list, batch processing, ALOS. This is a master image. And we're going to run step 3. We need an image list. Whatever list is put here is not going to use by this step anyways. And we're going to give it a config file. So it's going to try to compute the for every given point on the surface, its orbital info, what is range and azimuth, and then it's going to create a table and try to do triangulation. There's one more step over here, which is called offset topo. This is only used for very early data when the orbit isn't very good, and also specifically for L-band ALOS data, because sometimes you get a beam bended by ionosphere. So the geolocation might be off a little bit, and this step is trying to fix that. And now in the topo directory, you have this topo.ra.grd, which is back geocoded topography information, and also this topo shift, which is basically the topo RA after making this arrangement or making this adjustment. So the first 3 steps are done. We are ready to do interferometry, but we need to figure out which pairs we want to create first. Again, we're gonna add the image list and try to make it into a file called intf.in. And let's VI that file. So which pairs do we want to create? For here, I'm going to do these 2 pairs for sure, right? And we're also going to do that pair over there and maybe create a pair between these 2 as well. I don't know whether we want to keep this one, but just for testing to show you guys a result, we're going to leave it in. So we're going to make some changes over here. The first image, between the first image and the second image. And then between the second image and the third image. Yeah, this one, we want to keep it. Oops. Okay. And then the third image and the very last image. Then between the second image and the fourth. So 1, 2, 3, 4, 5. We still need one more, which is this one, right? All right, we have 5 radar images being put here. Of course, for other scenarios, we could also try to use automated script, for example, select pairs to try to select a network based on baseline, a threshold of baseline, or a threshold on temporal baseline, et cetera, et cetera. But for now, for this older generation of satellites, sometimes you want just to put in the ones that you want to create based on this baseline time plot. All right, we're gonna again edit this file, config file a little bit. Let's go all the way to the very end. I mean, for interferometry, we're just going to use the default parameters here. We're not going to change it. But we are not going to unwrap the interferogram. So we're setting the threshold snafu to be 0. And also we're setting this threshold geocode to 0. So we don't want to do like geocoding until we get the time series down. So we're going to do batch processing. Again, we need the master image and intf.in. We're going to do step 4 with the config file. This is interferometry, right? Okay, has started trying to run phase diff, which is doing interferometry. After that, there will be a filtering step. As this goes, you can also check what's being produced over here. So you get 2 more directories getting generated. One is INTF, which is a temporary directory where you're running all the interferometry, and also INTF all. So after things are done, it's going to get all the directory moved to this INTF all directory. You see things are being processed. So you see it's running, getting new files. Okay, things are done. I think I made a mistake because we have two lines that are listed exactly the same. So it only end up having 4 interferograms. But we're going to check on those interferograms first. And you see that looks sort of okay. It's crossing the creeping section. You can sort of see the creep over here. If you click on another one, you see some creep over here. Yeah, this one's a little bit noisy because this is the one that's getting aligned a little bit further away, I think. Wait, 2008, 025, and another one here. This is the one with very short temporal baseline, this one. So the coherence looks better, but also the signal is smaller. So that's pretty much what we are doing for the batch processing. I made a tiny mistake, didn't create this one. But I guess sort of you guys understand what's needed to be done in order to do batch processing for these earlier data sets. Okay, the next demo we will be doing is about Sentinel-1 data. Let's come here, and I have already downloaded some of the data sets. As you can see, they are listed here. Each days has, each acquisition dates, you have 2 of them getting downloaded. We're going to start by checking where do we want to process these data sets. You can do that by if you go into one of these directories. And you see a bunch of folders inside, annotation, which is the metadata file, measurement, which are the data. And there's a folder inside called preview. If you go inside, you see that there's a map overlay.kml together with a PNG file, quick look. If you open that, for example, we want to open all of them on this specific date, r/. You see that they're opening these on Google Earth. They are sort of covering this area, the Bay Area. But for TOPS data, it usually comes without really a definition of what we call frame, because it's a burst acquisition mode radar. Almost always, if you want to process data for a specific area, for example, your area of interest, you do want to sort of organize the data first before you really do anything. So what we're going to do is that we'll drop a pin over here to sort of let us know where our area of interest is. For example, I am interested in the creep on Hayward Fault. So I'm going to drop a pin sort of to the northmost side of Hayward. And then we're going to copy these coordinates back to here. We're going to create a new directory called organized, maybe. And we're going to make a file called pins.ll. We're going to paste these coordinates into it. Also the latitude. Don't switch these two, because if you switch, there might cause some problem. I've seen that many times already from the users. And we're going to move the pin to the southern end of Hayward, almost close to the creeping section already. We're going to leave it here and then copy these coordinates to the file. Also, when you're doing this 2 pins scenario, you need to move your pins along the orbit. For example, this is a descending orbit acquisitions. You're going to put your first pin sort of to the north and second pin to the south. If you have an ascending acquisition scenario, you need to put your pins at the southern side first, and then the second one to be in the north, sort of moving it along the orbit direction. Then what we're going to do is we're going to create a file list, PWD. We need to add the absolute path into the file list because of some of the limitations of the shell scripting that we have in GMTSAR. So what we're going to do is that we're going to ALOS this data /star safe. but we don't want to list anything inside, so we put a -d in front to just list the directories. And then we're going to redirect it into a file list. So now we have a pins.ll and also a file list. The script that we'll be running is called organize files tops.csh. If you are running not with Mac, but with a Linux machine, sometimes you need to add this. Instead of using organize files tops, you need to use organize files tops Linux, because there are some commands that are different on Mac and Linux. So we made some changes specifically for that. For this script, it asks for file list, pins.ll, and also a mode. We're going to run it right over here. Files tops, file list, pins.ll. We're going to run it with mode 1 first, because mode 1 says it's going to tell how many records are going to get generated, and mode 2 are actually going to do the organizing. And also, what we want to do is we will be picking the polarization mode to be VV, which is sort of the case for most scenarios. But if you go to the polar regions, you might have HH instead. Okay, it's trying to fetch orbit files from this website automatically. All right, it is done. The most important message that you can get out of this output is that it says, okay, frame on this date will be reorganized. That means based on the pins that you dropped over here, it goes through the list of files and think, oh, maybe you have enough coverage between these two pins, and then it's going to pop out this message. It's the same for other two dates as well, if you read the messages from the terminal. And the next step will be running this one more time, but now with mode 2 to actually do the organizing of the data sets. And because you have already downloaded the orbit file from the prior step, this is just doing the organizing, even though it is using orbit information, it's reading from the local files instead of fetching it from the internet. One of them are done. Also, when it is running, you see that it's telling you that we're extracting data from burst number 4 to number 10. So based on the pins you dropped on the map. Sometimes the number burst changes from one subsource to another, but that's normal. All right, things are done. If we do ALOS, you see that these are the orbit files that's getting downloaded automatically. By default, it's going to download the precise orbit, but as you know, that precise orbit takes time to be uploaded or processed. So for the very, very new data, you probably have to like do that by hand using create frame tops, which is another script. But normally for any data that's, I don't know, maybe 3 weeks old, this script will run normally. And other than these orbit files, you also have a new directory getting created. If you do a ALS inside, these are the reorganized data sets. So next, we're going to create a topography map, the DEM for processing the data. But this time, we're going to just read it from the map. So we're going to make a directory called topo. And then we're going to run this make dem.csh again. Using the bounds over here, this looks like 123. And this side looks like 119.5. And we're going to do 36 and 38.5 maybe. And we're going to run with SRTM 3 again, because that's faster. All right, things are done because I have downloaded these for this region before, so it runs really fast. Normally, it's going to take a while to fetch data from the Hawaii server. All right. Next, we will be processing the data. Because I'm interested in Hayward fault. You probably have seen that the first subsource pretty have no information in terms of trying to get anything from Hayward. So we're only going to process the second and the third subsource. So we're going to make a directory, F2, F3. For each of them, you have a raw and a topo. And for the topo directory, we're going to just link the DM files here. For the raw directory, we're going to link from the organized second subsource, VV polarization, and also the TIFF file, which is the data. We're also going to link the precise orbit file we just downloaded, and also need the DM. Do ALOS. Okay, these are all the files we need. Then next, we're going to run a script called prep data.csh. If you're on Linux, again, you need to prep data Linux, but we're on the Mac, so we're going to do it just like that. This is trying to get a orbit list from ASF, I guess. All right, it is done. If we do ALOS, there's only one file getting generated, which is this data.in. If we VI this data.in, you see that it comes with the data and also an orbit after that. It's the same for all three of them. So the next step will be running a script called preprog batch tops.csh. And if you just hit enter without any argument, you see that it requires this data.in, which is acquired from the prior step when you are running this prep data.csh. Also need the DEM and the mode. The mode 1 will be just running through all the files and give you a baseline table and provide you a baseline time plot. If you run it with mode 2, it's going to produce the PRM, LED, and SLC actually doing the processing. So what we're going to do is we're going to give it a data.in, dem.grd, and we're going to run it with mode 1. Should be pretty fast. Okay, it is done. Some more stuff getting generated, mostly just PRM and LED, which are the parameter and orbit file. If you cat this baseline table.dat, again, this stores the file name, dates, date from a specific date, cumulative through time, and also perpendicular and the parallel baseline. Because this is the early script, like I myself doesn't have a PS viewer on my Mac, so I'm gonna do a GMT PS convert. And then open and look at it. All right, this is the baseline timetable. Sort of looks okay, but still we want to pick this one to be the master image. In order to do that, we're going to open the data.in file, find this date. Oops. Okay, this is the second one in the list. We're going to move it to the top. So the first line will be the supermaster image. So next we're going to run this one more time, but now with mode 2. So it's extracting the data and trying to do restoration. While it is running, we're going to move to the directory here, F3. Let me open a new tab. We're going to do the same thing for the other subswaths. em.grd, go to the raw directory. W3, VV. Oops, made a mistake. // orbit files. Then we're going to run this prep data.csh one more time. Let's check how it is running. It's doing like coordination, geometric coordination. Do note that I didn't like try to run spectral diversity. If you are interested in using spectral diversity to enhance your so-called coordination, what you can do is that during this step, instead of running preproc batch tops.csh, you can run this esd.csh. Inside is going to run spectral diversity. It's going to extract the burst overlap area first, and then run spectral diversity over them, estimate the offset, and then update the coordination grid, and then run the processing again. And also, other than this mode, it also had the ESD mode specified over here. Depending on how you calculate the differences between or double difference phase between the burst overlap, you can choose to be doing average or doing a median. Or you could interpolate through the entire map using a green spline. These are like approaches that you can choose for doing ESD. Okay, this part is done. Let's run preproc batch. Oh, we need to VI this data in first. Put this master image to be at the front. Oops, did it wrong. Then we run this preproc batch top/sh data.in dm.grd. We don't need to run it with mode 1 anymore because we already tested things here. The baseline might change a little bit because this is perpendicular baseline being plotted here. It changes with local angle a little bit, but basically we're just follow the same like master image determined before. So set it running. Okay, while this is running, let's go to documents. Okay, while these are the coordinations are running, let's try to create a topo map for them first. If we go to F2, go to topo directory. What you can do is that, I mean, you could run just as in the nodes, like running step 1 and step 2, but you could also just do it by hand. So what we're going to do here is that we know that this is the supermaster image. So we're going to copy this over. Also copy the LED files over. What we're going to do is we're going to run this script called dm to topo.ra.csh. We're going to give it this master.prm, dm.grd. In order to make things run a little bit faster, we're going to do this triangulation again instead of doing surface, even though surface is a little bit more stable. You can do the same thing. This is F2. All right, this is done. You can do the same thing for the F3 directory as well. D with 1. So we're going to wait a little bit until this is done. It's running the topo generation step. So once you get really clear of what you will be able to do, you could do it my way. But if you are like a beginner and want to like go through every details, you probably want to follow the time series document. We have them online. Okay, the topo generation part finished even before the coordination step. And one way of checking like this map is you can do an NC view on topo.ra.grd. So this is sort of how it looked like in radar coordinates. You can make it larger, but it's sort of like upside down though. Yeah. So I guess all of them are pretty much done. So next step, we will be doing a like creation of interferograms. Inside the raw directory, we have this baseline table. So we're going to copy it over. In order to create interferometric network, what you can do is that you can do a select pairs. It's going to ask you for a baseline time table. You need a threshold in time. Let's do, I don't know, maybe 120 days. And for threshold baseline, which is a threshold for perpendicular baseline, let's do 150. It's going to give you something that's called the intf.in file. Okay, you see you have 3 interferograms here, but you also get a new baseline.ps generated. If you do a GMTPS convert, and open this baseline .pdf file, they are pretty much the same as before, except you have all these interferograms plotted on the map as well. Next, what we're going to do is that we're going to copy a config file over. If you know where your GMTSAR is installed, it's usually here, user local GMTSAR, your GMTSAR directory, and GMTSAR CSH, star batch star. What we need is, well, this is not the best way of doing it. Batch star. We need this batch tops config. We're going to copy this over and then edit it and set things running. We're going to do a vi batch tops config. Since we already generated this topo RA, we don't need to run step 1 anymore. We don't want to start from step 1. Instead, we want to start from step 2. And we know the master image is this one. We just set it over here. All the rest, you probably don't need to change the default parameters, except we don't want to do GL coding for the moment. We're going to do merging of the subswaps later on, and maybe after that, do the time series and then do the GL coding. That's sort of how things work. So in order to do that, we're going to run this command called intf tops. We give it the intf.in and also batch tops config, set things running. Okay, it's running. It's the same as when you are doing the doing the for ALOS data, but we have some specific changes for intf tops. Essentially, this step can also be done with batch processing because things are sort of like in the transition from like each of these script to sort of like universal batch processing script. Both of them should work okay. While this is running, we're gonna also work on the other track. I mean, the other subswaps. We're just gonna copy over because we have already interferometric pairs for F2. We want to do the same thing for F3. intf.in over here, F2. And also the batch tops config. Or if you way add this, we're going to change all these F2 to F3 by doing a %s. Then all of them has been changed to F3. We're also going to edit the batch tops config file by changing the master image being 3. All the parameters, all the rest of the parameters should remain the same, right? But this time, instead of like running like one after another, we're going to do a sort of like parallel thing. What we're going to use is this script called intf tops parallel, where you can do intf.in batch config. You also need to specify the number of cores or number of threads you want to use, like sort of spreading the jobs to different threads using GNU parallel. Because I'm running this on my laptop, I'm going to use 2 instead of putting a large number behind. Okay, it's running multiple of them behind. You should be getting a log file for each of them. If I check again in this directory, you'll find out that it's basically spreading this intf.in into each specific interferogram. So each of them has intf.in. And those that are running has a log file going on. If you cap this log, you see how things are running. Okay, it's making amplitudes right now. So we're going to wait a little bit until everything's done. Okay, things are done again. The stacks of tops interferograms are finished generating. This is the parallel part. As you can see, if you just do ls intf all, you see that you have 3 interferograms generated as shown in this baseline.pdf. If you do ls on the other subswaths, you also have 3 interferograms generated here as well. So the next step will be to merge these interferograms together. But before that, you can look at this INTF all and see inside and check on the interferogram, see how things are going. You see that the radar phase looks okay. Also here as well. Same here. Also for the F3, you also have interferograms generated here and here. Yeah, so that looks okay. Next step, we will be trying to merge these together because you want to like put the data processed in one subsource and the other subsource together before you do phase unwrapping. What we're gonna do is that we're gonna do a make directory merge. The script we'll be using is called merge batch because this is batch processing. What it asks for is an input file that has this kind of like format where you have the pass PRM file for the master and PRM file for the aligned, for the second subsource and for the third subsource, if you have multiple of them. And also a config file. For the config file, we could just copy the F2 batch config here. And also for the input file, there's a way of generating this, which is called create merge input.csh. It requires your INTF list. What we're going to do is we're going to do ls f2 INTF all into INTF list. So we're going to run this create merge input. We're going to give it an INTF list. The path will be .. I guess. Oh, actually just .. And because we're gonna run for 2 and 3, the mode will be 2, just by reading this notes over here. Okay, it outputted this. We're gonna redirect it into a merge list. One thing very important to note here is that normally when you're doing this batch merging, you have to put a pair with the master image being your supermaster image to be the very first line. But since I made a mistake, we only have 3 images here, and I picked the last one to be the master image, so I can't do that anymore. So that was a mistake. Normally, you need to put a pair with your master image, for example, this one to be your supermaster image, and put it to the very top. That's what's supposed to be done. Let me try to move this to see whether things are working or not. So next, you will be running this merge batch. We give it a merge list and also config file, batch config. So another thing is that you notice there's an optional parameter here. Sometimes when you do this merging, there might be gaps between the subsource. When that happens, you can turn on that DET stitch. So it's going to try to figure out where to stitch things together. But if you don't specify that parameter, by default, it's going to stitch in the center of the overlap between the subsource. So we're going to just run this. We also need a DM file. It's going to recompute the projection matrix. Okay, it finished first one, so it's running this projection. Let's wait a little bit. All right, the merging is done. If we do ls in this directory, you see there are 3 directories created during the merging process. You also have a new, what we call trans.dat, which is a projection lookup table computed here. And inside each of these merged directory, you see that they have something created, mostly just for the coherence, phase, and mask. If you want to check on whether things are working fine, you could do a quick NC view on this grid and see how things are running. This is the face. Let me change the color table. Maybe black and white. Seems the merging ran okay, even though we didn't put the supermaster image to be on the top line. Sometimes it's okay, but in order to avoid certain issues, that's always the thing you want to do, like put the master image to be on the very top of your merge list. So seems things are okay. So we pretty much have finished processing the stack of data. You have the interferograms. So the next step will be to doing phase unwrapping. You could run like snafu to unwrap them, or run a unwrap parallel .csh to do parallel phase unwrapping. After it's unwrapped, you can do time series. So that's pretty much everything for the batch processing part.